Hello everyone, welcome to the video. Today we are going to solve the problem kth smallest element in an array. In this problem, we are given an array. We are also given L and R, which denote the starting and end index of the range in which we have to find the kth smallest element. And we are given a k. Then we have to find the kth smallest element in the given range for this array. We will try to solve this problem. We will not directly jump to the solution, but we'll try to see step by step how to build and reach to the solution. We discuss the questions of data structures and algorithms on this channel in simplest words with fundamental approach. If you are new to this channel, please subscribe. To begin with, let us first note the key things provided in the question. We are given an array. We are given L and R, which denote the range in which we have to find the kth smallest element. We are given a k and we are asked the kth smallest element. We are also given that all the elements in the array are distinct. So let us understand this with an example. Let's say this array is given to us and the range is from 0 to 5, that means the complete array, and we are asked the third smallest element. So which will be the smallest element in this array? 3. But bigger than that 4, and bigger than that is 7. So answer is 7. Now if we consider our solution as black box, we are given an array as input, a left and right index as input, a k as input, and we have to return the element. So our function signature would look something like this, taking ARR, array size, L, R and K as input, and it returns an integer. Now, before jumping to the solution, let us try to see how are we finding the third smallest element in this array. We first look for the smallest one. We see it is 3. Then we see a number just bigger than this, 4. This is the second smallest one. And then we go for a number just bigger than this, 7. It is the third smallest one. So what exactly are we doing? We are sorting the array. So what does our approach look like? We can first sort the array and then we can return the element ARR L plus K minus 1. L is the starting index of the range from where we have to find, and K minus 1 will be the index of the element that we have to return. So L plus K minus 1 will be the required index. Now what will be the time complexity of this solution? It will be big O of n log n, because any efficient sorting algorithm takes big O of n log n. But is this efficient? We are here sorting the whole array while we don't care about the elements that come after the kth smallest one. So that is definitely not efficient approach of sorting the whole array. Now that we know that sorting the whole array is inefficient, so we can do is that we keep the only k elements sorted, the smallest k elements sorted. So let's say we saw the first 3 elements of the array, we sorted them. Now till the first 3 elements, the third smallest element is 10. Now let's see what do we have to do when we move to the next element. Now the next element is 3. Now among the 4 elements, can 3 be part of this array? Yes, because 3 will be among the members who are the smallest k elements. So when we see 3, the new array will become 3, 4 and 7. 10 will go out. So this array will always maintain smallest k elements that are seen so far in a sorted manner, and the last element will denote the kth smallest element seen so far. So now what does our approach look like? We first create a new array of size k. We sort the first k elements and put them in the new array. We then iterate for the remaining elements of the array. In every iteration we have one element. We compare it with the last element or the biggest element of our new array. If this current element is greater than this, that means it cannot ever be a part of the k smallest elements. Otherwise, we insert it into a correct position like 3 here. And once this all is done, we return the last element here. Let us try to understand the time complexity of this approach. So since first we are sorting the first k elements, this will take big O of k log k time, right? Once we have sorted, we are iterating over all the remaining elements. So it is like big O of n minus k, iterating. Now for every element, we may have to insert it into this new array, and to insert it into the new array, we may have to travel k positions. So for every element, we may have to spend big O of k time as well. So this will be our new time complexity. But even this is not efficient. Why? Because in every iteration, we are keeping all the k elements sorted, while all we need is the kth smallest element after every iteration. Now that we know our previous approach was also inefficient, let us first try to see where we are in the problem. So what we basically have is that we have a fixed size collection of data, right? What is that fixed size? K. And what do we want out of it? First thing is we want that the maximum element we should be able to find very quickly. Now, in this case, in sorted array, we are able to find the maximum element in big O of one time. We just have to take the last element. But there is second requirement as well. It is possible that there is a new element coming. Now this new element may need to be inserted into our data collection. But since the size is fixed, an old element will have to go. Now this removal of old element and insertion of new element, how much time was it taking in sorted array? It was taking big O of k time. Why? Because to insert the new element, we have to find the appropriate position by traversing linearly across the array. Can we optimize on that? Is there a data structure that can give us the maximum element quickly and also update its collection by removing old and inserting new in lesser time? Now, array took linear time, that is big O of k, for step 2. Yes, there is one data structure, and that data structure is heap. Heap always keeps track of a maximum or a minimum element, so it can give us that in big O of one time. And updating a fixed size heap by removing an old element and inserting a new element takes big O of log k, which is lesser than big O of k. Now, what does our new approach look like? Now, instead of sorted array, we will use heap. We will have a heap of size k. We will build first k elements into the heap. Then we will iterate for all the remaining elements of the array. And in every iteration, we will have an element. If that element is greater than the heap's current maximum, that means it cannot be among the k smallest elements. And if it is smaller, that means we have to remove the maximum from the heap and insert the new element into the heap. Once this loop is done, we can return the heap's maximum, and that will be our kth smallest element. Now, what will be the time complexity of this solution? First of all, building the heap with first k elements, it will take big O of k. Then we have to iterate over n minus k elements of which are remaining in the array, and for every element we will take big O of log k for the insertion and removal in the heap. So this will be the overall time complexity, which is much lesser than our previous solution. And the space complexity for this will be big O of k, because we are using a heap to store the k elements. This is a very common technique where if we have a fixed size data collection and we have to track max and min, which can max or minimum, which can be updated as we insert new elements, we can always use heap. Let us now try to see the working code for the algorithm that we derived. First of all, we initialize a heap, MaxHeap. MaxHeap in Java is corresponds to a class called PriorityQueue. MaxHeap and MinHeap both correspond to this class. So we first initialize this and we pass collections.reverse order because by default a PriorityQueue initialized is a MinHeap. So we have we have declared this MaxHeap here. Then we first add the k elements from L into the MaxHeap. By this time we have the MaxHeap ready with the k elements in it, and we can access the maximum element in the MaxHeap in big O of one time. Now we iterate for the remaining elements in the array till the R range and in every iteration we get the current element, and if the current element is smaller than the maximum element present in our heap, we remove the maximum element from the heap and insert the new element. And as we return from this, as we complete this loop, the max heap contains the kth smallest element, so we return that. You can also find the link to this code in description. To summarize, we first understood the problem with an example. Then we came up with the simplest approach. We thought, let's just sort the whole array and we can return the relevant element. That way we came to the time complexity of big O of n log n. We realized that it is inefficient because we don't really need to sort the whole array. Therefore, we came up with a second approach. We thought that let's maintain a new array in which there will always be smallest k elements in a sorted fashion. And as we travel across the original array, we will keep updating this new array with the smallest k elements seen so far, which are sorted. And at the end of the traversal of the original array, we will have the relevant element at the end of the new array. This gave us the time complexity of big O of k log k plus big O of n minus k into big O of k. But we realized that even this was inefficient because insertion in array for the new element at appropriate position was taking big O of k time. Therefore, we came with third approach in which we used heap instead of the sorted array. And in the heap, insertion and removal takes big O of log k time. That way we were able to save on the time complexity. Then we also saw the code walkthrough in Java for this question, and you can find the link in description. This is it for this video. We'll meet again in the next video with some other problem. Thank you for watching.